it's not an attractive force. It's really just a glue type force. So it's a different nature than the back.
It has a short life, does it mean it's more radioactive?
Yes. Yeah, that's the way, when you say more radioactive, that's what you're thinking of.
So when you're talking about adding protons or adding neutrons, are you talking about doing that actually, or are you talking about in theory? In other words, is that something that can actually be done? And I guess my next question is, doesn't the number of electrons have to increase if you do that? Like, in other words, if you went from hydrogen to helium, I think is number 2, would that then have 2 electrons?
It can have 2 electrons, and it normally would. So if I have electrons around, then sure, those electrons will say, will want to be there. And it will naturally, it's sort of more natural state is to have 2 electrons if it has 2 protons. But it doesn't have to. We're really just talking about this nucleus. The answer to the first part of your question is either way. We talk about it as, if I take this and I add 2 neutrons or I add a neutron, when I'm talking about it, I'm really just talking about if I had a thing that had this other number. But the way we test these things experimentally is you build an accelerator and you come up with a process where I can actually just start adding neutrons to it. It's not as clean as, let me just pluck a neutron and put it there. I have to go through some other process that hopefully we'll have a chance to talk about later in the course. But really, that's what we're doing. We are creating new things by adding them. And that's part of why we know where this is up here, because I can get up here. The experiments to do that are possible. I can add protons fairly easily, because I can throw protons around. Neutrons, since they don't have a charge, I can't move them around, I can't do anything with them. They're really hard to control. And so I don't have a way experimentally to be able to just start adding neutrons to something. There are some ways I can do it. I get down here, but I can't really get very far.
Neutron star, why does it emit a light if in fact actually it's nothing but neutrons hanging together?
We'll get to that later.
Okay.
There's a few things we need to know before we get there. Okay, so what happens when I get this is basically the pictures now of what my nuclei look like, and it's this big ball. Here's a good one. It's just a ball of blue neutrons, red protons. They're not blue and red, but that's just the way they're drawn there, so you can tell which one's which. And that big ball keeps adding and adding, and I can get different numbers. I also get different shapes, because what I have here is the balance between those 2 forces, which is the whole story. They don't always line up as an evenly distributed ball. Again, this is the toy model. They're not actually little balls like that, but it's fine to think of them that way. So what happens is the distribution may not be even. So I don't get a sphere. I can get something that is squeezed into a shape like this. There's different shapes that they can get into. And in addition to that, it doesn't have to actually all stay together as a ball. It just kind of has to stay in the same vicinity. So I have anything like this is called collective behavior. It's one shape that's just kind of mushed one way or another. I can also have single particle behavior, where the shape looks like this. I have a couple of them that are hanging around outside. Now, these are still fairly close together. The electrons are way out there. Right? The electrons are nowhere near the nucleus. Again, if the nucleus is the size of a nickel, the electrons are the size of the Earth into where they were. So there's a huge distance between this and this, a huge physical, real-life distance between these things. But within the nucleus, so still within this ball, it can really look like I have one little ball and then a couple of them hanging around the outside. And so that's one of our, we have a few Nobel Prizes here. That was this guy, Modelson, in '75. Most of these guys I have pictures, there are pictures of him out there, but because he was on a stamp, I thought that would be the basic structure of the nucleus that we've been talking about now, that toy model, that ball, that was Wigner in '63. A lot of physicists, especially this kind of stuff, the second half of their lives, after they do their great work, they kind of go on to other things. Einstein spent most of the second part of his career trying to figure out how to get gravity to fit into all the pictures that we're talking about today, and still nobody has done that, so it's a little bit of a we'll have to use J's or something that's hard to do. Newton, much longer ago, spent the second half of his life on alchemy. Wigner was a little more in the mainstream there, but instead of focusing on the physics, his interests drifted more off to the philosophy of physics stuff, which is can be interesting. We're talking about here for the most part, but he did write a book, which is I I'm not necessarily recommending, I haven't actually read it yet, but I will, I just discovered it exists. The unreasonable effectiveness of mathematics and the natural sciences. Why does the math actually correspond to the physics? For us, when we come up with the math, we say, you do the next set of math, and then you go look for what that is physically, because it must correlate somehow. And everything that we do in physics is describable in the math, and it all fits. And you work in this for a while, and of course that's what it is. Math is the language of physics, and that's all there is. But he had the time after his Nobel Prize to sit here and actually contemplate these questions, and really worried about, why that would be. And then Hans Bethe, in '67, he got the prize for stellar nucleosynthesis, which is the other part of this question. You ask, how do I add neutrons to something? The real question is by doing it in stars. So let's get to stars. So I'll leave that there for now. We can do this. Okay. So stars. Stars are not special things. There's nothing special about a star. It's regular stuff. Just made out of you and me and everything. If we got enough of us together in one place, we would turn into a star. The reason this happens is that I have, what I have as a star is a whole bunch of stuff. I have enough stuff that I have gravity pushing it. This is kind of the first time that gravity has become important. These things all have mass, so they feel gravity, they're squeezed together. They're small, but if there's a whole lot of them, I have a whole lot of gravity pushing everything together. Now I have something different than what I've been talking about. I've been talking about the balance between the two forces. We have the electromagnetic force, which is repulsion, pushing me apart. And then I had the strong force, which is glue. Not really attractive, just glue. Now I can add gravity. And this is attraction. This is a new thing for us. Now I have a force that always attracts. It doesn't matter what my electric charge is, it doesn't matter what my strong force charge is. Or electric charge, I can be plus or minus. Strong force, right now we're talking about glue. In a couple of weeks we'll talk about the different charges there. There's actually 3 of them, not just plus and minus. Gravity only has one kind of charge, essentially, and it's all attractive, always attractive. So the more stuff I have, the more I'm squeezing together. And I had this picture of a nucleus where I had a proton, a neutron, and the protons are pushing apart, and the neutron's kind of gluing it together. And now I have gravity that's coming in to squeeze things together. This does something. This means that if I have more protons than I'm allowed to have, I'm still kind of okay because I have gravity squeezing. I have another force on my balance sheet. If I have enough of that, then I can squeeze things together that don't want to be together. I can overcome that force, and I can join 2 atoms together, 2 nuclei together. I have a proton here, I have a proton here, and because they're both positively charged, they're going to push apart, and in the normal world, they never come together. They're separate things. They're 2 hydrogen atoms. But if I have enough gravity, if they're in the center of this giant ball of stuff, then these 2 protons will be pushed together hard enough that it overcomes that positive repulsive force. The attractive force of the gravity pushing it in, and I have the electromagnetic force pushing it out. If the gravity pushes it enough together, then I can fuse them together and get them close enough that the strong force can take over. Because remember, the strong force only works at close distances. That glue, this is a very short range force. It's only if they're really close together. So if I have them out here, the electromagnetic force always wins. I get closer, and it's harder and harder and harder to push them together. In order for the strong force to win, they have to basically be touching. They have to be right up against each other, because that strong force is very, very short range. Gravity will let me do that. It will get me over that hump of repulsion to the point where the attraction takes over. So it's not just the number of protons versus the number of neutrons, it's how far apart these things are. We'll say about that here, small aside, is that that's what limits, that is what limits how big I can get. That's why this chart ends. At the potential super heavies, that potential, island of stability. The reason is, when I get so big, huge, the neutrons out here, the protons out here, can no longer feel all the strong force. They're too far away, because the strong force is so short range. And it's really just the electromagnetic force then is able to take over, because that's infinite range. That's what limits the biggest possible atom I can have, biggest possible nucleus. Because that strong force is too short range, and the nucleus itself actually gets bigger than the range of the strong force. And that's where I limit here. That's why when I talk about fission, we're always talking about uranium, plutonium. Those are out here. That's why those things break apart. That's why I have fission. Because at that edge, not just that I have too many protons compared to neutrons. It's not because I've moved too far out this way. It's because I've moved too far along this line. And so the range of the forces, rather than their strength, is what makes the difference. Okay. So when I get to stars, all that really happens, if I get enough stuff in one place, that there's enough gravity to squeeze it together, I will start fusing the different nuclei together. I'll have enough gravity that I overcome that repulsive electromagnetic force, and I'm able to squeeze things together to get them close enough that the strong force can take over and then they stick. So it's a push, I got to push it, and then you get over the hump and they fall right together, and that's fusion. When they fall together like that, they want to be together, because the strong force, that attractive force is much bigger. It's a lower energy state. It takes less energy to stick together than it does to be apart. Getting there is hard. I have to push and push and push and squeeze them. And once I do, they come together like magnets. The glue takes over. And that releases energy. And that energy is the energy of fusion. That's what fusion is. And it gives off all kinds of energy. Tons and tons of energy. Because the mass of that thing together is lower than the mass of the two things apart. So that's the mass being converted to energy when they come together. And that energy that comes off, that is the heat of a star. That's why a star ignites. That's why it's light and it's bright. I have something like Jupiter, almost big enough, but not quite big enough. It doesn't have enough stuff. If I took Jupiter and I added some more stuff to it, it would get heavy enough, there'd be enough gravity that it would be able to have this fusion reaction take place. It would squeeze these things together tight enough that the strong force could take over. I'd have nuclear fusion. It would be like a nuclear bomb going off in the middle of the thing, and that bright light, that heat, that is what a star is. That's all it is. There's nothing special there. It's regular stuff squeezed together by gravity until I get fusion, which is the same fusion in the nuclear bomb, fusion bomb. Okay.
So the strong force exists independently of a neutron. You can have two protons, if you bring them closer together without a neutron, still there's a strong force there that will trigger.
Right. Neutrons, protons, the things that are made up of, quarks and gluons, all feel the strong force. Electrons do not feel the strong force at all.
I actually busy in the relationship between stars and nuclear bombs. Can you go again?
Yeah, okay. So let me go through the stars, we'll see. Stars in here. So if I take, the key thing here is the balance between the two forces as a function of range. So if I have these two things, okay, there's a force pushing them apart. So as I push, I have to push harder and harder and harder to get them closer and closer and closer together. And the range of the strong force, let's say, is just if they get to this close. So the closer together they get, the harder I have to push. So I have to push harder and harder and harder and harder and harder. This is how hard I'm pushing. And then once they get this close, then the balance switches, because I'm inside the range of that strong force, and it sucks in. And not only do I not have to push, let's say this line here is I'm not pushing at all. I push harder and harder and harder and harder as I get closer and closer and closer together. And then they suck into each other, and I drop down. And now I have extra energy that I didn't used to have, because these things actually wanted to be together. It was because of the strong force. They really want to be together. They'll give off energy if they're together, but I have to get over that hump. to get there. I have to get past this repulsive force. And when I get past that repulsive force and I suck in together, it gives off energy. The energy that it gives off is enormous. And that's fusion. That's the heat and light comes off, all that energy comes out because I've gotten that. It was really because they wanted to be together. Because the strong force was so much more strong. They really wanted them together. That is fusion. And it's that process that happens inside stars. And the reason that happens only inside stars, for the most part, is that that's where I have enough gravity to get these two charges together. That's the pushing, the squeezing together comes from gravity. And that gravity happens in the middle of stars because I have so much stuff to squeeze it together.
Now, this is a constant process that lasts.
This is a
that many
constant
years,
process,
so we
right.
can see the light that they emit.
Yes, so this is a constant process that happens in stars. And it starts out, the easiest thing to get together is when I have 1 plus, 1 proton, 2 hydrogen atoms. That's the easiest thing, because I've only got 1 charge. So I have enough gravity, that gets started. The explosions inside, that fusion inside, that nuclear bomb that's going off inside the sun, pushes against gravity. And the sun balances out. So the size of the sun is determined by how much gravity I have squeezing in, because the gravity would want to just keep going. But this fusion process, it spits off so much energy, pushes it back out again. And so it's a balance. What happens eventually is you run out of hydrogen. I run out of things to fuse together. And now I don't have any more hydrogen. I don't have any pluses and pluses in there. I only have the things that I made from squeezing them together. That's helium. So now instead of plus and plus, I have 2 plus and 2 plus. And those things really don't want to come together, because I've got twice as much repulsion. So the fusion stops. And when the fusion stops, gravity says, hey, I got nothing pushing me back, and starts squeezing together more. When it squeezes together more, that's more squeezing, it gets strong enough, that squeezing gets strong enough that now the helium and the helium come together. And it starts happening again, and the sun pushes out a bit. And it squeezes down again, and it pushes out again. I move up through the periodic table, I move through all the elements, making one element after another after another. And in the same case, it's the same process. What happens is the sun runs out of one fuel, fusion stops, it starts collapsing, that more squeezing means I can do the next harder thing, and it pushes out again. And I go through that process, and it keeps happening again, 2, 3, 4, 5, all the way up through the periodic table, until I get to iron. Once I get to iron, it changes. This picture is different. Now, when I squeeze them together, I don't get any energy out. I have to add energy in order to squeeze them together. It's the opposite. Iron is that point where the thing gets big enough that repulsive force and that attractive force have balanced. And I can no longer get energy by squeezing things together. And I no longer have fusion, and the star dies. So what will happen with the sun is it'll reach that point, it'll run out of everything up to iron, it'll be made mostly of iron, and then we're done. The whole thing stops, it just turns brown, and that's it.
So quickly, so you introduced the gravity
Yes.
concept. You described everything in terms of particles and waves. They
Right.
both. With gravity, just show the arrows. Is gravity neither a particle nor a wave, or we don't know?
We all believe, with perfect faith, that gravity has particles called gravitons that move back and forth and make it happen, and that the charge of gravity is what we call gravitational mass. We have no evidence whatsoever for this. We keep building bigger and bigger machines. It's hard to build a gravity detector machine because we don't know enough. But because everything else works together so nicely, gravity must. And by analogy, it just fits. It fits, but you can't find it. We'll find it.
So one more follow-up question is on your chart there where you get to super heavy
Yes.
and then it ends. Isn't that where you get it to black holes?
No. Black holes is a gazillion times more of this stuff. Black hole is, so what we talked about with a star is that I keep making things until I make iron, and then I'm out of stuff. And the star kind of just dies out. So I got 2 problems. Right? One, the biggest problem is we have things that are heavier than iron. Iron is 55, which is like halfway up here. Iron's right around here. So how do I get all these other things? Where all the rest of the stuff that we're made out of, lead, gold, uranium, everything, I mean, most of all kinds of stuff, we don't have. There's only one way that can be made. Not exactly only one way, there's basically one way that's made in the universe. When I have that star and I get it all iron, I'm at the top, and I can't get any more energy out by fusion, it'll start shrinking again and kind of just die off. If it's really, really, really heavy, the gravity kind of runs away. It just starts squeezing really hard, really fast. And when that happens, again, supernova. The thing explodes. It looks like that. What we have here is the supernova in the middle, and the explosion spews off all this stuff, because it's just an enormous explosion that happens. When I have that enormous explosion that happens, I can cheat. It's so hot and so fast. Okay, the problem I had here was that we talked about, if I add a neutron, if I add a proton, it'll fall apart. If I add 2 neutrons, it'll fall apart. Let's stick with protons. I'm at that drip line. If I add a proton, the proton doesn't stick. It decays in some number of, as we have here. You see the time scale for these things is maybe seconds, minutes. So I can't make these things above here because they'll fall apart. But if I have a supernova, it's so hot, I got so many protons flying around, I can keep adding atom, not atom, but add them, over and over again, and before it has a chance to fall apart. This is called the RP process, the rapid proton process. Inside a supernova, I can just shoot up here, and go boop, 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 boop. And now when I decay, I don't decay straight back down to where I used to be. I don't just give off protons. Those protons will change into neutrons through various decay processes. And instead of moving straight up and straight down, if I shoot up far enough, I tend to decay diagonally on this chart. When things break apart, when they give off stuff, the radiation that comes off, it doesn't come off up and down. It comes off to the side. It comes off diagonally. So by adding protons really fast and dropping back down, and adding really fast and dropping back down, I can kind of wiggle my way in a diagonal line up. And that's what the RP process, which is the rapid proton process, and there's an equivalent neutron process, the R process, that happens only inside supernovas. And in doing that, I'm able to kind of zigzag my way up.
So at what point in that timeline would meteors form? Is it once it becomes iron and then it would?
That's
Is it part of
4
that
billion
process?
years later. What happens is
400 years later?
400 billion years later. Not 400 later. 4 billion. What happens is all this stuff that's out here will start coalescing into chunks of other things and make new stars, make new solar systems. So what we're made out of, the reason we had to have this happen first before the Earth could form. Otherwise there wouldn't be anything heavier than iron. The Earth, there wouldn't be any uranium. There wouldn't be anything else. It's made in these supernovas. So this is really the process. Z is proton number. I can keep adding them and they decay diagonally, and I can zigzag my way up through that periodic table. Forward.
Do we know where in this process of fusion and gravity and changing towards lead our sun is? Do we know where?
Yeah, our sun is, it's a relatively light star. It is, how far along the process? Yeah, it's still burning hydrogen. It's still at the beginning. It's burning some helium, but it's not quite near the beginning. But one of the best understood things in all of physics is the solar model, the way stars work. Stars are, once you get this far, stars are incredibly simple. And all the math works, everything works. It's what we predict, what we observe matches up completely exactly. There's really no mystery. So we know how old all the stars are, we know how old the sun is, we know how long the sun's going to live, really, to the day just about. It won't be days once the sun's out.
So no time too soon.
Right, not too soon. You have a few billion years left. So this is the periodic table, which many of you have probably all seen before, may be familiar with. What I liked about this is that this particular version is, rather than tell you all the chemistry stuff that you normally have a periodic table, this tells you where these things were made from. So the Big Bang, which we haven't really talked about, but the Big Bang, the beginning of the universe, starting from nothing, I've got hydrogen in it. That's really all I've got. That's it. Someday in another course we'll talk about how the universe started, because that's also interesting. Then as things were flying around in the universe, I was able to make the first other very light elements there. Because cosmic rays flying around, bouncing, just things flying around was enough to overcome a single proton, maybe 2 protons together, get them squeezed together. That was possible. Once I get really above that, then I get to a point where I have to start making these things in stars. I need that process of fusion going on constantly. And I get up through these other lighter elements, somewhere up the first row or two. And some things are easier to put together than others based on the shell structure. But once I get above iron, which is right here, so I can only get to here in something like the sun, in a regular star. I need a supernova to get anything past that. This whole thing needs a supernova. It's only those first two rows that I can make in a regular star. So we can't have been the first generation of stars. There had to have been a generation of really large stars that had to be born, live, and die, and then our Earth and Sun be formed out of the remnants of those dead stars for us to have any of this other stuff here. The one point I'll point at the bottom here, the stuff that's in here is not made in any natural process. That's all stuff that occurs just in things that we've been able to make through accelerators and reactors and that kind of stuff. And so one last point that I want to make is on fission, because we talked about fusion. That's what fusion is. Fission is when I'm way out at when I'm way up here, and the thing splits. Essentially by itself. It splits because, now it's of the balance of how big it is. It's too big, so that my strong force, which maybe I can feel between here and here, maybe that's the range of my strong force, but I'm so big that the proton out here and the proton out here, they can still see that electromagnetic force because that's infinite, but they're outside of what the range of the strong force can be. And at that point, the thing cracks in half. Jane?
But can't neutrons be added to the outer ring? In other words,
The
why
neutrons,
do you have to, the strong force is also dependent somehow on if there are neutrons
Right.
present.
so if the strong
Can you
force,
structure the ball, so to speak, so that you don't
there is some
go
structure.
outside of this range?
There is some structure, and that's why we get to the super deformed nuclei when we're up here, stuff that has weird shapes. So you can get a structure like that. So that does happen. But there still comes a point where, if the strong force covers the whole thing, then I can kind of average over all the neutrons.
Mhm.
But I get to a point where I really can't do that anymore because I need more neutrons than I can physically pack into that space. These things are really fixed size when we talk about this. Even though they're not, that's the twin model, but they are. They're fixed size here, when we think of it this way. So this thing will crack in half, but what happens when it cracks in half is it doesn't just split evenly. It splits in such a way that other extra pieces come out. So one of the things that tends to fly out is neutrons. Because this line here, between the number of neutrons and the number of protons, it's not a straight line up here. It's not, I had one neutron, I had one proton. I always have more neutrons. The heavier I get, the balance between neutrons and protons was more and more in the neutron favor. Because of this problem, because of the needing to add more neutrons to overcome the shorter range and the strong force. So this line kind of bends down as we go. What that means is, if I take something heavy and I divide it in half, I'm going to have extra neutrons left over. Because the neutron-proton ratio is balanced here. These are 1-to-1. See, this starts out straight, and then it gets more neutrons. And then I have to keep adding more and more neutrons relative to the number of protons. So if I move down here, I have too many neutrons, and extra neutrons. Those neutrons, when something splits, I didn't mean to draw that way, that's a crack, not a photon. When this thing splits, a neutron will come off, another neutron will come off. This thing splits, it's got a lot of energy. It's giving off a whole bunch of energy. These neutrons that are flying out here have lots of energy. If they hit something that's kind of big and fat and kind of wants to break up anyway, that's right on the edge, it's going to crack it in half. And that'll give off two neutrons. And they tell two friends, and they tell two friends, and they tell two friends. So what happens is I get a chain reaction where these neutrons keep triggering each of these other nuclei to crack, to split again and again. And each time it splits, I get more energy and more neutrons. And this keeps happening until I run out of atoms to split. So I run out of everything that's unstable. That's a fission model. That's nuclear fission. This does not happen in stars. This is, we talk about atomic bombs or nuclear bombs being the stuff of stars or capturing the power of stars. That's a fusion model. Fission is not that. Fission is just doing this. Now, these things are unstable to begin with, so some of them will decay on their own. They will crack on their own even if I don't do anything. I can trigger it with the neutrons, but even if I don't, they'll decay at some rate. So I can make a bomb, I can make a fission bomb, just by getting enough of this stuff together, and it will start by itself. If I have enough of these free neutrons floating around, this will start to happen automatically. So you hear stories, there's things I won't get into now, but where if I get a big enough pile, boom, that's all I need to do. I don't need any technology. All I need is enough of this stuff. The way the bombs actually work is I have two piles of the stuff that's almost enough, and I put some explosives around it to squeeze it together real fast, and then I'll trigger that happen. This actually happened once in the history of the Earth. naturally. There was a deposit in Africa of lots of uranium. And when some kind of earthquake, something shifted,